Hello and welcome, everyone. It's nice to see so many faces and names across the screen. My name is Lisa K. Schweier, and I am the Program Manager for Mobility 21. We'd like to welcome you to today's Smart Mobility Connections seminar. The series is sponsored by Traffic 21 and the Mobility 21 University Transportation Center here at Carnegie Mellon University. It's an opportunity for faculty to showcase their current transportation projects, and it's also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster future interdisciplinary collaboration. Please note this session is being recorded and all participants' microphones are muted. To ask a question, you simply need to send a message through the chat box. I have talked with Umit, and we are going to hold the questions till the end of his presentation, but feel free to go ahead and put them in as they come up. So now I would like to introduce today's speaker. Professor Emeritus Umit Ozguner is a well-known expert on intelligent vehicles and intelligent transportation systems. His career of over 40 years, he's been contributing to various aspects of IV and ITS as a researcher, educator, and through other volunteer service to the ITS community. He has been an author or co-author of more than 500 publications, which have had over 16,000 citations. He holds the title of Fellow in the IEEE for his contributions to the theory and practice of autonomous ground vehicles, and is the founding editor-in-chief of the IEEE ITS Society, Transactions on Intelligent Vehicles. In addition, he received the Lifetime Achievement Award from the IEEE ITS Society. His research has been and is supported by many industries, including Ford, GM, Honda, Renault, and the DOT's University Transportation Centers. Please help me welcome Umit Ozguner as he tells us about his University Transportation Center project, Vulnerable Road Users Dominated the Shared Spaces with Vehicles. Umit?
Thank you, Lisa K, for that introduction, and happy to be here with all of you, and happy to see a number of names and faces that I know, and hope to tell a few things about the work we have been doing. So with that, let me see if I can share my screen.
Okay, perfect. Perfect.
Looks good. Okay, I guess we're all here and onwards. So today I'd like to, as advertised, talk about pedestrians and vehicles sharing the space and kind of lead towards a thought about the vulnerable road users, as they're called, pedestrians and others, how they will be possibly dominating this shared space, at least in designated areas. I'd like to thank everybody that I worked with through these years that we've been doing work on pedestrians and other VRUs. Professors Redmill, Dr. Yurtsever, and a number of students and postdocs that have been involved with this. Some have graduated and left, and hopefully contributing further. Okay, this is sort of a standard classical slide that we always start with, and it's getting old. And it shows that percentage of total fatalities, a substantial component of pedestrians, over 10%. So that's something we don't like, and we would like to see what we can do. Now, pedestrians and other vulnerable road users, VRUs, encounter road vehicles in what we call a shared space, where the VRUs are at a distinct disadvantage. If there are many pedestrians, a crowd of VRUs and the vehicles will slow down and pedestrians will step away. At some crowd density, the vehicle may stop and wait for crowds to cross or disperse. Okay, this seems to be going faster than I'm talking. Is that automated? Interesting.
We don't have any control over the slides, Umit.
Okay. Apparently I don't either. Let me see if there's, okay. Oh, maybe I'll just have to keep in this mode. Is this okay? Can everybody see the slide?
Yes, we can see it.
Okay. Timing seems to be now in my control. Okay, there are two types of problems that I'd like to address. Before that, let me go back one slide and say that the talk will be sort of three parts. I will have to go over some background work we have done and reported before. So some of you may, in fact, have seen some of the slides that I'll present, but it's inevitable that I have to rely on some of them to point out what you have been doing recently and my thoughts about the future. So after the background, we'll talk a little bit about our recent work, and then have a few thoughts about one possible future. Okay, I'd like to distinguish a little bit about individual pedestrians crossing the street type of operation, or attempting to cross the street with a lot of cars, and then pedestrian crowds in shared spaces. And there is certainly in that picture that you see on the right side, you see a lot of pedestrians, and it has even reached the point where the pedestrians kind of dominate the space, and the cars, which look quite threatening in the picture on the left, and pushing the pedestrian to run across the street. But on the right-hand picture, it's the pedestrian's world. So how do we get from left, and how do we solve the problems on the right is a problem that we'll look at. So one common aspect is the individual pedestrian's motion. We will be modeling a pedestrian where it will have a destination. A pedestrian would like to reach a goal position, and it will interact with not just the approaching vehicle, but also possibly other pedestrians that are moving with it, if there indeed is a group. So we'll look at what collective pedestrians' motion is going to be, and how that will change under the vehicle's influence. Okay, this is kind of a busy slide, and I was a little bit concerned, but I'd like to point a few things that we could have. Infrastructure-based sensors detecting where the pedestrian is, or we could have, as part of that infrastructure, it could be a UAV-based camera, a roadside camera, or something mounted on the pedestrian that could tell everybody around where it is or where it is moving to. We could have the on-vehicle sensors, LiDAR, stereo cameras, monocular cameras, and so on. And these could be on the ego vehicle. That would be the one concerned about the pedestrian, but it could also be getting information from sensors on nearby vehicles. We would have to talk about a high precision map, maybe, that would give the feed into the positions and orientation of individual pedestrians. So we have all these participants in the overall world, and we can address it with an offline approach using simulation results, or we can be looking at an online approach where the autonomous vehicle itself will have to be the decision maker and decide on what to do. So there are various problems in this setup. There's the autonomous vehicle driving strategy planning, and there's the scenario prediction that has to be done by the autonomous vehicle. We have to estimate the goal of the pedestrian. We'll have to see about interacting with the crowd. And certainly we have to also look at the vehicle model. Okay, again, this looks like a busy slide, but it's kind of a summary, and I'll address some of these in separate slides later on. One thing I would like to point out is this little figure on the top right corner, where we have one way, kind of a simplistic way of seeing the effect of a vehicle's framework sort of affecting the pedestrians that may be surrounding it. We're interested in this because we're interested in scenarios where the vehicle, as you see in the sequence of figures, where a vehicle may be going into a crowd, that crowd having maybe one, maybe two destinations, and moving at a specific angle with respect to the vehicle and the vehicle's trajectory. Again, I'll give more detailed versions of this. This is just sort of a summary of where we're going. Okay, the pedestrian's behavior has to be considered. There are various ways of looking at that. We can estimate its behavior using various modeling approaches, social force, or just online estimation and trajectory determination. We can make assumptions about how one pedestrian affects another, and how, of course, they both are affected by the car. And you can see our model of the car here at the model of the effects of the car on the pedestrian here on this simplified figure on the bottom left corner. Next comes the motion planning and control possibilities for the car itself. And this may be different when we have a single pedestrian walking across our trajectory, and by our, I'm taking the part of the vehicle. There can be one pedestrian walking across our intended trajectory, or there could be lots of them. And we have to plan our trajectories accordingly, or just stop and wait. Again, I'm going fairly fast over these. This is all sort of summarizing earlier work, and just to see what sort of setup we have been considering. Okay, we have had an interest in cars and crowds of pedestrians for a while now, and this has led us to try to get some data on such behaviors, so that we can take a look at data collected and decide how to fit sort of dynamic behavior attributes to each pedestrian that's coming in front of us or near us as a car. So we have to do detection, tracking, intention prediction, and so that this will affect our control for the vehicle. There are various data sets. This is an older slide, and it gives the names of a few data sets that were that existed. Nowadays, there have been a few more that are in the public domain. So this is by no means all that's available. But when we started this, these were the ones that were available. So we felt the need of generating a data set ourselves. So let me talk a little bit about the data sets that we established. We established some data from experiments that we did in our backyard, so to speak. And then one of our postdocs that returned to his country in China from Dalian University of Technology did some data collection there and got us some nice trajectories that we have been using since then. Okay, so with that, let me first show a little bit about the data set we generated at the Ohio State campus. In fact, at the parking lots behind our lab, and hopefully this will work. Okay. Okay, these are all students from our lab and a vehicle being driven through them. And you can see that the pedestrians sort of disperse as the vehicle is going through them. Now, you may say that everybody's conscious that this is an experiment. On the other hand, there's nothing particular that will change their behavior from the natural behavior. So that was the type of data that we collected. Let me now go through the data collected by our postdoc in China. This is a more interesting case because A, the participant pedestrians are not coached or aware of what's going on, and B, there's a lot of pedestrians. One thing that, well, there are a couple of observations that one may make. One is the pedestrians almost dominate. There are some that step away, and there are some that don't and expect the car to slow down and wait anyway. So let's take a look at this group. And you may even notice one case where one of the cars kind of moves away from the pedestrian. As you can see, the pedestrians don't seem to be too perturbed by having a car amongst them. Here's one where the car actually moves a little bit away. And here you can distinctly see that the car makes a slight motion away. Right there, yeah. Well, I always enjoy seeing these behaviors. Okay, so based on all of these, we can provide a social force model, as it's called. It's the origin of all other rule-based models, still popular after more than 20, 30 years of its introduction. And it's frequently used in crowd motion simulation. It has explainability, adaptability, and scalability. And in theory, fewer parameters means less amount of data for calibration and training. We added the vehicle influence into that type of model and adjusted, redesigned pedestrian interaction mechanism, calibrated it and validated it. And this was done as part of the work we did for this UTC. Okay, based on that, based on the data collected on that, we generated their own simulations. And here I'll show that we first look at just crowds moving against each other. And here we introduce a car. And you can see the pedestrians stepping away. Let's go to the slightly different setup where the pedestrians are moving north-south and the car is going east-west. So one of these simulations where the car and pedestrians were moving on the same axis, and this is a different one. So one can generate these type of patterns about how pedestrians and cars behave in a shared space. Okay, now I'll step back and take a look at just a single pedestrian trying to cross the street and a bunch of threatening cars, in this case, moving towards it. But of course, one has to start at the very beginning, which would be just a single car approaching a single pedestrian. And the pedestrian wants to is at the waiting area and has a destination across the street. And there are sort of three phases of this operation. It's going to the waiting area, deciding to cross or yield, and then crossing the road. Has to find the right moment to cross the road and has to hopefully make sure that it's not hit by a vehicle. This is from the pedestrian side. You can also look at the problem from the vehicle side. We're assuming a longitudinal motion only, so there is no dodging. Avoid the crossing pedestrian, keep the desired speed as much as possible. So in the simplest problem, this is what we have to solve. So there is the framework for the vehicle pedestrian interaction that let's talk about first. We're considering a three-layer architecture. There's a perception, there's interaction, and then there's the motion. And you can see it, various things here from the pedestrian. And the assumption, the physical states, position, velocity are known to each other. modified pedestrian motion model called multi-state social force model. We added a state transition module, crossing decision-making, and simplified the vehicle influence. So let's look at this little framework here. From the vehicle side, it has to do a pedestrian motion predictor, has to do its own longitudinal speed control, and of course it is governed by the vehicle dynamics. From the pedestrian side, the pedestrian has to do gap estimation, assuming there's some distance that it'd like to see before the car is totally on the pedestrian. If there is more than one pedestrian, then we have to do multi-state social force interaction. Would you be pushing the other guy away? Would you be following it? Would you be trying to hold hands or what? And of course, the pedestrian dynamics governs what happens accordingly. So that's the general framework of crossing the street. And we did a number of experiments. Let me show sort of what is happening. Vehicles approaching and the pedestrian is crossing. And we have done a ton of variations of this, both from the vehicle standpoint or the pedestrian standpoint, and have observed various different types of behaviors. And I'm just showing you a single pedestrian and a single vehicle. You can add more vehicles, you can add more pedestrians, and complicate things with multiple lanes and in other threatening situations too. Okay, a little background also on the occluded pedestrian problem. What you have seen, what I've showed in the couple of slides before this was pure crossing behavior. We do have what we call the occluded pedestrian problem also, where we don't know that a pedestrian may be coming. And this is quite a common situation. One of the cases we looked at in one of the many different autonomous taxi exercises is going. I'm trying to be careful with my words there. One of the many autonomous taxi test exercises going on around the world. We were involved in one of them, and there was a lot of concern there about occluded pedestrians that may be emerging from behind vehicles. And there was especially one case that the car manufacturer was very concerned about driving in front of a school, and that some small children may run out from behind cars. So that sort of affected our thinking about some of these problems. And I'll return to that point in a little bit. So here is a problem that we looked at for a while. What should the automated car driving along the street do when there are a bunch of parked cars behind which pedestrians may be lurking? And the density of the visible parked cars and distance to the closest one may be known. The density of visible pedestrians and distance to the closest one may be known. And the distance, if there is also a crosswalk, if it is visible, can improve the performance of controller for occluded pedestrian scenarios. Specifically for places where the GPS accuracy is low, tall buildings, crowded metropolitan area, we have problems. So you can see in this figure here where there are visible objects, including these visible pedestrians kind of approaching the curb, and there are pedestrians that may or may not be behind these parked cars that are occluded. And we deal with the emergent pedestrian problem, where you have to estimate the probability distribution that a pedestrian may emerge. And of course, this probability distribution may be unknown or not very reliable, and may be biased depending on the time of the day and certainly the location that we're at. I mean, if there is a school right behind this, whether there is a pedestrian crossing or not, the school behind certainly biases the probability distribution and our attention to it. So again, we had considered a lot of different types of controllers for the vehicle. As you can see, there's the little pedestrian here, not quite deciding to cross, and the car approaches and there is a pedestrian crossing, but it decides that the pedestrian will not cross. But here, there's a pedestrian that didn't use the pedestrian crossing and decided to jump out onto the street anyway. In this case, we managed not to hit it and slowed down. Here's another episode. And here is, again, our pedestrian is dawdling on the curb, and we decide this time to slow while we're crossing it, and obviously, and this one I think we hit it actually. So a lot of studies on these types of scenarios were done to decide on what sort of decision-making approach based on probabilities and probability distributions that we know we should, the autonomous car should be talking about. So that gives an idea of our background. Some of you may have seen some of that or read about it, and I felt I wanted to go over it because it sort of shows you where we're coming from. Now, I have about 3 pieces of more recent work that I'll now talk about. One is, you just saw a whole bunch of straight road driving issues. Of course, another favorite of all of us is the intersection situation, and we've spent recently, last almost 3 years, I had a project from an insurance company, interestingly enough, that wanted to know if they inserted what they called a smart pole, which the smart pole would have a camera, and the camera would see a pedestrian that was crossing and would send a warning signal to approaching cars. Again, this could be an occluded situation. For example, in the photograph here, you can see that it's kind of a narrow street. This is in Japan, incidentally. That's why the car is on the left lane of the street. It's going to make a left turn, it certainly doesn't know if there is a pedestrian right around the corner. So if there was a pole with a camera and a wireless connection, it can help, but we need to see what the variations could be in the vehicle's trajectory. Here is a version that you see on the left, where we have shown maybe 3 of the possible trajectories turning left, and each one ends up slightly differently and may or may not hit the crossing pedestrian. And this is related to also something called the car assessment program in Europe. Okay, simplified cases. The car can itself detect a pedestrian crossing, or it may be occluded due to this building right there where the car's sensors can't see a pedestrian that intends to go north. So the car, if the car makes a fast right turn, it will run right into the pedestrian. Or where you see the little star there, there could be our so-called smart pole that could have a camera on it and then see the pedestrian that's crossing or intending to cross and send a warning to our car that's approaching, or any other car for that matter, so that even though our car doesn't see the pedestrian as a impending threat, it will hear about it through the wireless connection. There are many variations of this problem, and we looked at some of them and tried to find how much this smart pole and the technology could reduce the risk of hitting a pedestrian. And well, I won't go into the details, but various bad things can still happen, including losing the wireless connection or the camera not detecting the pedestrian and so on. So we analyzed all of that for the sponsor and came up with a analysis of the risks and how much risk. Again, remember that this was sponsored by an insurance company. So assume they were happy with the results, and we tried simulations, number of collisions in, what is this, 108,000, almost 109,000 episodes that we looked at, and certain number of these cases ended up with a collision. And we could see, I mean, the numbers may not physically represent true what is going to happen, although 108,000 is a pretty high number. But you can see that certainly with the smart pole, the collision rate would be reduced a substantial percentage. So whether it affects the insurance, of course, is not what we look at. We just provide these types of numbers about how the collision rate is reduced with, and whether that's enough or not to invest in this is a different question. And we look at variations of the speed, the friction, variation speed of the pedestrian, and whether there's rain and all sorts of other variations to come up with the 109,000 different episodes of simulating. We did build a special simulator for this. Okay, I won't go into the details of the analysis of why the collision occurs and so on. But we do have techniques to do that. Let me skip over that. Of course, the right turn with the building in between is not the only scenario where this may become important. Here you see a couple of other, it could be turning left and not seeing this guy on the left side crossing the street from south to north, or it could be, well, just blocked off with a truck that's crossing. And if you are sort of just approaching this without braking, as soon as the truck departs and you make a left turn, you may still be hitting that pedestrian. So again, there are many variations that the same type of event could happen. And I won't go further into that, but we do have our approach to analyzing. Okay. Another thing that we did during this last year was looking at, again, an emerging pedestrian and emerging VRU that may be approaching our car's trajectory, and it may be either out in the open or may have one or two cars in front of it. These are from low-speed automation LSAD systems for predefined routes. These are the typical test cases that we looked at, and we have been looking at these types of tests and what we can say about those. Okay. Oh, I'm skipped one slide. Let me go back to that. In all of these, one of the issues has always been what information is supplied by the system about jaywalking or other situations. So we started to look at look for a metric where the worth of provided information can be determined. And we looked at an entropy-based metric to assess various things. One of the things was accuracy of PNT information, but again, the important part is trying to find the metric. How you can use that metric may be different. So if you have a metric, you can tell that if the following information can be supplied, then how useful will that information be, and will it be worth our effort and investment if we invest in the extra sensor that would be giving us that information. So after looking at various ways of finding a metric, we have kind of decided on using some entropy-based metrics that seem to give us information about the investment that may be worthwhile. So, okay. Another thing that we looked at was, or one or more of our researchers looked at, was an adversarial testing process. This was to determine what is the worst case scenario that you can get with a pedestrian. And here we're thinking is sort of a almost a fictitious problem about if you have an adversarial pedestrian that is sort of intent in trying to hit your car, what is the worst that can happen? Can he run after your car and throw himself onto the car? And that would be an adversarial pedestrian. It certainly could represent maybe somebody that's drunk or something, or somebody's trying to show off on a campus roadway, or being happy about the fact that their team won and so on. But anyway, this is now sort of a popular direction, and we wanted to look at whether adversarial pedestrian training, at least from the simulation viewpoint, can tell us something about how safe it is for our autonomous car to be driving. And there has been work that's been done and still ongoing about such pedestrians, how you can have adversarial pedestrians to test the car's autonomous driving for a worst case scenario. I mean, what's the worst that can happen? Well, the worst that can happen is the pedestrian running after and throwing himself at the car, and that if you can make sure that the car will stop even then or get away, then you can sort of guarantee that your autonomous vehicle can work in this type of environment. So we don't recommend, certainly are not doing this to aiming towards a real implementation, but just checking about how fragile is our autonomous controlled decision-making mechanism. So that's still ongoing and a learning approach for the pedestrian. I won't go into the details because my time is getting less and less. So let me switch over to say a few words about a vision for automated personal mobility. So the title of my talk was Towards Dominance of the VRU, of the pedestrian. So I would like to throw at you some ideas that I have been spending some time in developing, and see if you have some reaction on this. So a vision for personal mobility which satisfies a number of goals. Claim that you want to aim at reduced car-based traffic in the center of a smart city. Want to operate without crowded streets with crowded vehicles and easy melding with robot delivery related activity, and use pedestrian roadways purely if we want, and feed into larger automated vehicles on highways. Direct utility for people who have mobility problems, can be used as fleets with door-to-door individualized service. So I propose a 3-level radial hierarchy with the innermost circle, if you will have pedestrians and personal platforms. And the second would have platforms within vehicles that would be regulated in their activity. And then at the outermost edge, there'll be free flow of vehicles. So we can start with what I call an automated personal indoor-outdoor mobility platform. And vehicles for individuals with mobility issues can be used, or something like that can be used. Here we see the present use of these types of platforms where somebody elderly or having problems with mobility can call, and the platform can come to the person and take the person to, at this point, to a bus stop. And The unified theme would be you can have this inner circle of platforms that individuals can ride or robots that are doing deliverables at the same time and using the same sort of area. And at the second layer, second radial layer, you can have these platforms entering vehicles that can carry those platforms, which would be vans or buses. And certainly, even at this time, we have human-assisted mounting with ramps or lifts into such vehicles. And then we can have sort of single-person driving platforms themselves, could be regulated, and we can show certainly that these are what the energy and fuel usage of such vehicles could be in transforming a certain number of people around. This is not 100% entirely brand new thought. Here's a very old picture from, I believe, an Italian magazine from last century. And you can see that even then, people were thinking about individuals driving around on these types of platforms. So I'll leave you with that thought and these an image of these platforms, and I'll stop at this point and address any questions during the few minutes that remain. Thank you, everybody.
Yeah, thank you, Umit. And I've never seen this picture before. It's kind of fascinating and a little frightening, but we did get a couple questions in, so I'm going to give them to you in the order that they arrived. The first one is about pedestrians who are blind or have vision impairments. Do the vehicles emit sounds so they can be located by people with vision impairment, or how will people with disabilities be accommodated or taken into account for this work?
Well, I'm not sure whether that refers to sort of the stuff that I said we have been working on and so on, or in this last vision.
It came in the earlier part of your talk when doing the research.
Okay. Well, I mean, my last vision sort of answers some of those, because it certainly came about when we were looking at various vehicles like these that can accommodate some of the mobility constrained individuals. So that may answer that question, but certainly a lot of our research can address specifically different mobility constrained individuals' problems.
Yeah, I think the question specifically was about vision, of not being able to see the vehicles as they're approaching.
Yeah, well, we have to use some technology. We haven't actually looked at that ourselves, considered that ourselves, but certainly there's enough technology around that one can focus on those types of issues. In this case, which I'm showing, one can certainly insert technologies that can help the vision impaired. I was thinking more of the walking impaired people, but certainly any other constraints about mobility could be accommodated.
Okay, thank you. So our next question is, how do you classify jaywalking? Communities that live on a collector road or even arterial sometimes have to paint their own zebra crossings for their neighborhood,
Yeah.
which is often referred to as tactical urbanism, or have to cross illegally to get basic food and healthcare nearby. Should we blame the pedestrian in the first place, given that streets were designed before the automobiles came?
Well, that's a good question. Our whole research in this relies on having an estimated pedestrian emergence of probability distribution. So I think, and we can discuss that offline too. There are two different problems here. One is the jaywaker's rights. Do we know anything about the emergent probability distribution of a jaywalker? Are there locations where you're more prone to getting jaywalkers? In which case, have to do something about it, whether it could be, as in this case that we are looking at, the probability distribution of somebody appearing in front of you has to be embedded into the vehicle's driving pattern, or there has to be other sensors placed so that externally some sensor can detect that there is a jaywalker and send a warning to the car. But again, having prior probabilities of emergent jaywalkers may help. Now, as far as drawing crossings, I don't know the answer, or I don't know how to deal with that at this point. But certainly we have the tools to look at some of these problems.
Thank you. And a final question for you about students. We often have students involved in these sessions, and they're interested many times in looking at pursuing this field for their own future careers. If you were to say two pieces of advice that you would give students who are looking to move into ITS, work in transportation, what would those two pieces of advice be?
Well, my one piece always is, look at what people have established through the years. Don't ignore that, and look at the engineering that has gone into it. Look at the work that has already been done, and don't ignore that. Don't come in with totally sort of things that may look in paper but people have addressed before, or there are certain practical reasons that they can't be implemented. That's sort of the general advice that I give, and that certainly goes for transportation, and immediately pumping in the latest and greatest sounding technology into your solutions. Certainly, there is wonderful new technology there. Certainly, there is more computing power that's there, but that doesn't mean that the first hot algorithm that you see can immediately be useful. So respect what has been done, respect the engineering behind it, and then go in there with an inquisitive mind and be aware of the new resources and capabilities of the technology. That's and it covers like two things.
I really appreciate that. Thank you so much. And thank you for being here today. I'd like to thank all of the attendees who were here. We did get one other question we didn't have a chance to answer, but it was about data sets. So I'm going to ask the person who is interested in that to let us know. We can point you to the research documentation where you will be able to find that. Also, as I mentioned earlier, the presentation today is going to be posted on our What's Happening page, as well as on our YouTube library channel. You will also be receiving an email asking you to take a short survey about today's session. And our next SMC is going to be on Friday, January 20th. We will be taking a little break between now and then. Please watch for your invitation to join us. Again, thanks for attending today, and please feel free to let us know if you have any other questions. Thank you again, Umit.
Thank you.